Euclidean geometry, theorem proof, angle and alternate segment, also known as alternate segment theorem and often referred to as tangent chord or tan chord. If a tangent is drawn to a circle and a chord is drawn from the point of contact, so there's the point of contact, there's the chord, then the angle between the tangent and the chord is equal to the angle in the alternate segment. In other words, this angle between tangent and chord is equal to the angle subtended by that chord on the alternate, the other side, at the circumference. Now there are two angles between the tangent and the chord. There's the one, there's the other one, the red one. And that is also equal to the angle subtended by the chord in the alternate, the other segment on the circumference. So therefore that angle equals that angle. Let's just look at the reasoning behind this before we go into the actual proof. Notice that this is now changed. Instead of saying angle between tangent and chord, it now says angles between tangent and chord. So now we start, as we have before. Theorems build on previous theorems and definitions. So what can we use at this stage? There are certain circle theorems we can use, but if we start with a tangent, we say, well, tangents, there's only one theorem we can build on. And that is the one that says that the radius to the point of contact is perpendicular to the tangent. That's the only one you can use to link it. So now, but in order to link it to the circle theorems now, that radius sitting in the middle means absolutely nothing. So we're going to have to produce it to there. We're going to have to draw the diameter, because now we have right across the circle, and we're going to join across to that angle in the alternate segment. I'm going to join across that way because now it involves the angle. Some people do a proof where they join across this way, but this seems more logical. Now we can go to circle theorems and say, well, what circle theorems can we know? And immediately we see a diameter, and diameter should set off a thought pattern that says, hang on, diameter means angle in semicircle. So that is a right angle. Angles in the same segment. If you have a look here, there's this familiar bow tie type pattern. And so therefore that angle is equal to that. So look what we have now. We have a right angle, we have a right angle. So this is equal to that. But hang on, we have a blue dot and a blue dot. So what's left must be equal to what's left, because they're both 90 minus the blue dot. So let's do the theorem itself. This theorem must cover both parts because it's angles. If you're required to prove one where it doesn't say angles and just angle, then you can just do the one. So this theorem's in two parts. We have the one part with the angle there and the other part with the angle here. But let's deal just with the angle on that side first. So given. We're going to have to say given because remember that given, we only need given in a theorem proof if we need to state something that cannot be shown in the diagram. We cannot show that CBD is a tangent. While it looks like a tangent, it may not be by 1 degree. So we say given CBD tangent at B. Required to prove. Well, we're going to try to prove that the angle between this chord and this tangent is equal to the angle in the alternate segment. So required to prove interprets it. Interpret the theorem statement to the diagram in question. So while the theorem statement talks about the angle between the tangent chord and angle in alternate segment, the required proof actually states it in the letters of the diagram. Construction. Now remember, when we were doing it earlier, we were looking at, we need to link the tangent to the circle, and the only way is through radius tangent theorem. And so we drew the diameter, and we joined to the actual vertex that has the angle in the alternate segment in it. So now our proof. GBD is 90 degrees. There we are. Reason, radius tangent. Radtan, we abbreviate for short. Then we have another 90 degrees there. So we have BPG equals 90 degrees. And the reason there, angle in semicircle. So we now have those two angles equal to one another. Now we're going to look at the ones. B1, but, we're arguing this, but B1 equals P1. The reason being angles in the same segment. So we now have this angle equals that angle, and we have those two angles in the same segment. So if you remember from the previous screen, that means the remainder must equal the remainder. Therefore B2 equals P2. We don't give a reason because it's axiomatic. It follows automatically. It's an automatic thing. It's mathematical logic. Now that's that diagram, and it's proven. But now we have to prove for the other angle. So let's start with a new figure without all the confusing other lines in it. And we're back to this where we've kept this one. We've already proven that angle ABD equals angle P. And we're now going to prove that angle ABC equals angle Q. Required to prove ABC equals Q. Proof. It's pretty straightforward. P plus Q is 180 degrees. Opposite angle cyclic quad. And we have C1 plus B1 plus B2 equals 180 degrees. B1 plus B2 equals 180 degrees. Reason being adjacent angle straight line. So we have P plus Q 180, B2 plus B1 180, but B2 equals that angle P, proven originally. And that means what's left, once again, what's left, which is the B1, is equal to what's left, which is the Q. Remember that you only need to do this part if you're told to prove angles. But if you're given a diagram and told to prove the one, then you go only as far as the end of the first one.